For a number of years, there has been a specific way to put a server inside of a rack and make a data center, but we're finding that there is a better way to build a mousetrap. Facebook is doing it with the Open Compute project. Now, we asked Facebook if they'd come on camera and show us how they're doing their data centers, and they said, no, we can't go on camera. So the solution is, William and I have just spent the last hour going through this entire rack with the Facebook people, and so him and I are going to do the best to present it. So I guess, William, we'll start with this. What is the reason for having a new rack? We've done it the same way. What makes this better?
So for a large hyperscaler, someone like Facebook, they can afford to change up almost all of the rack designs to meet the efficiency requirements and the cost requirements of their data centers in a way that is maybe more optimal than the standard 19-inch rack. So for the rest of the industry, it made more sense where everyone has the same standard rack, and because they had to interoperate, they weren't able to really play with the form factors or play with the different types of sleds and switch and power configurations that someone who has sort of more budget and more flexibility where they have their own data centers, they now have this ability to play with this stuff.
Facebook has a ton of videos and pictures that people are storing, so they need a lot of processing power to process those videos. They need a lot of storage to store all of that data. Amazon, for example, needs just a lot of processing power. They don't necessarily need any GPU performance, not much GPU performance, and they don't necessarily need a lot of storage. So this rack can be completely configured one way for Amazon and configured a completely different way for Facebook.
That's right, yeah, absolutely, it's great. So yeah, Amazon could adopt this, Google could adopt this, Microsoft could adopt this. All the specs are online at the Open Compute Foundation. They have links for Facebook stuff. Every one of these designs that you see here does have PDFs, it has board schematics, it has everything.
Now, one of the things, they've actually put a lot of thought into how they're going to put this rack together, so you'll notice as we go through this component by component, all of these things are toolless. It means the data center techs can get in, get the problem fixed, and get back out. We're also going to talk a little bit about the onboard controllers, the OpenBMC modules, that are going to allow these machines to talk out to the data center technicians, and they will actually be able to track tickets and identify problems before even a human has noticed they exist. So a fan goes out in the back, they don't have to have a data center tech walking around to see if the fans are running. No, it throws an alert, and that OpenBMC controller will contact and file a ticket on its own and say, hey, help me, one of my fans has died. So this is probably a cluster as compared to what you would probably see in production. It would be more, singularly.
It would be more homogeneous. So you'll see here in our overview, there's going to be a lot of different types of machines in this rack, but you wouldn't normally see that kind of configuration in a Facebook data center. Yeah, they'll space those things out. Like you'll have a whole bunch of GPU compute doing one specific set of tasks. You'll have a whole bunch of storage maybe. You may just have a whole bunch of regular CPU compute type nodes all in one area.
We'll start with the actual rack design, and then we'll go sled by sled and show you what each one of these devices do and how they're put together. Let's take a look at that. Let's start with the actual design of the rack itself. Now, the rack is a different dimension than your standard 19-inch rack.
That's right. If you look at this rack, it's actually 21 inches wide. You'll get a better shot from the front where you can see they've actually installed switches that are 19-inch compatible but have little expanders to fit the 21-inch rack here.
So the rack itself actually has this back plane, and inside of this you can actually see there's two silver bars, and those are actually providing 12-volt power to the entire rack. So this power supply unit, which actually contains also the battery backup for the UPS, is supplying DC power to the rack, which eliminates a lot of the power inefficiencies that you'd have in a traditional rack because you're not converting from AC back to DC, back to AC, back to DC as we get into the components. All the components in the rack are going to be DC. The backplane of the rack is DC, and so we just make that conversion once as we take AC power in, convert it to DC, as well as provide the DC power for the battery backup.
Yeah, that's definitely something that's interesting and different from your normal rack, because on your normal rack, you have UPS battery banks that are going from AC to AC, and then you're incurring the loss of going through the UPS and incurring the loss again when you go into the server. And the other nice thing about doing DC in these centralized locations, you'll see there's one up here, and there's actually one, if I reach down, there's one down here. If you do it in these centralized locations, you can have more efficiency gains by having larger rectifiers, and then your larger battery banks and stuff, and you're not going back to AC again and all sorts of other sort of points of inefficiency.
We'll go through as we get back to the front side. When we pull the sleds out, you'll be able to see this. Certain sleds actually have a rail tray that come out towards the front. So some of these sleds can actually stay powered on even while they're being serviced. We'll start with, I guess, William, why don't you show us these fan designs, a modular way to replace fans quickly?
Yeah, so what's really interesting, something they've done here is they've added the fans on the back here, and they're not actually attached to the trays that can be pulled out the front, and all you have to do is unscrew the fan, and it pops right out of the thing. So you can take the fan module out, and if the fan breaks, you just unscrew it from the back, no tools needed. There is a screwdriver thing on here, but it's a thumb screw, and then you can just take that, plug it right back in if you have a new one, and screw this thing down. Now, they've actually optimized this in their future designs. You'll see down here, if I go and I pull on this fan unit, they've actually added in a handle and a lever so that you don't even need to use a thumb screw anymore. And it's got both of the large fans on it there, and they plug in through the back plane, and you get the same metrics, you get fan speed, all the stuff right to the BMC. All the designs that are kind of incorporated into this rack is it's meant to be cost efficient, so they're kind of removing pieces they don't need. Everything's very kind of industrial, and I wouldn't call it unfinished looking, but it's just not fancy like some of the enterprise hardware you see where they have these weird, cool, whimsical designs and stuff going on. This is all very functional and robust, and it's cheap, easy for techs to replace, all the things they want in the data center where they're managing thousands of these machines.
And the standards are open, so anybody can implement this.
Yep, and you can't necessarily tell whose it is unless you've seen it before, right? Like you can't know this is a Facebook server without having asked people at Facebook or people who know and are familiar with the matter. It doesn't say Facebook on it or anything.
Let's dig into the actual components that go into the rack and show you how that works. All right, so let's start with the actual top of the rack. And again, like William said, you can see here, these are standard 19-inch switches, but they have adapters that actually expand them out to the full depth. Now, the truth is they're not standard 19-inch switches. These are actually something pretty special.
Yeah, so what's interesting is they've actually adapted the power supply modules so that it'll pass the DC from the back of the rack, back of the power poles that we just saw before, straight through into the switch without requiring the inverter to AC and then rectifying back down at the switch level.
And the switches aren't just normal switches, they're actually white label switches that are designed with open standards as well.
That's right, so there's a company called Barefoot Networks as one of the vendors who will make these and sell them to your retail. And I believe, if I'm not mistaken, and I've looked at the designs in the past, they're just Broadcom switches on the inside. They're switch ASICs from Broadcom. There's an x86 board in there based around an Atom or a Xeon D platform, and then a BMC to go with that. So it kind of fits into their typical server design model.
All right, William, let's take a look at this very first one. Go ahead and pull that out.
All right, so here is a disk tray that is just a disk tray and a controller so that you can get SAS out to a machine above it.
So let's start with that. So in a traditional server, you would have a processor and a disk and a graphics card and a network card. In this case, this entire tray is basically just a big disk.
It's JBOD, just a bunch of disks. You got a controller here for doing your external SAS, and it's probably got a switch chip so it can do more SAS than what is subscribed here on the port. And you would connect that up to one of the machines above it as a host, where it would host all the disks to the network, presumably. All right, now let's pull out the other tray that actually has a host attached to it, because that is one of the options we have with this design. So you'll see here, this one you can see the memory modules on top, and the CPU is kind of contained within, but this host was attached to the same exact tray of disks, but now you get a network connection out, so you can connect the disks directly to a network with a presumably fairly low power CPU, like a Xeon D or an Atom or something. And then you get all of the 15 disks of capacity in one of the open compute rack units of space.
All right, we're back to the front of the rack. Let's take a look at the power supply units, because like I say, this is pretty interesting. It's handling both DC and AC. So this, I assume, is where the battery units would go. And then above this is where the actual power supply units are. Tell me about those.
Yeah, that's right. So you can actually see on here, they haven't included the battery units, but they are required to run a rack. And you'll see there are actually labels on the front. It may be too far away, but they put the batteries below the power supplies. And we can actually take these power supplies out without any tools, like everything else on the rack. And it's a giant monster of a power supply that supplies power for, I don't know, maybe 15, 20 machines between all three of these power supplies.
Yeah, the average
you can see on the back the hefty banks because they have these huge metal rods that go to the 12-volt rails in the rack, and then you can see some of the inputs there as well.
The average power draw, power budget, as they put it, is 10 to, I think you said 10 to 12 kilowatts?
That's right. You have 3 of these up here and 3 below, so between all 6, you're doing 10 to 12 kilowatts.
Now, the batteries are required, like you said, to run the unit. Now, that's not actually a physical requirement. They've actually enforced that in firmware.
That's right. So if you actually were able to look at the back of this unit, there's a management controller, and it is able to tell you the status of these power supply units and the status of the batteries, and it's able to run tests on the batteries to make sure they're performing optimally, can drain them down, bring them back up, make sure they don't explode, those sorts of things. So it can be doing testing all the time and ensuring this thing is running optimally.
What's this next sled that we have down here?
Yeah, so the next sled is kind of similar to the first one we talked about. This one was hard disks, and it was all SAS or SATA based. This one is actually all NVMEs, so it's your newer tier of storage. So if we pull this guy out, it'll look fairly similar to the one above. So it's going to be 15 disks wide and 3 deep, so you get, 5 disks wide, 15 total. And you'll see that it has a similar but newer connector for the disks. And you'll see there's a lot of metal going on here. And so if we take one of these out, which apparently we are unqualified to do, you'll see it's just a metal tray, and it hooks up with your typical U.2 style connector on the back here, and then we can take off the top piece to expose the insides, and it just fits standard M.2 drives inside of this guy.
So whereas the other sled that was doing regular hard disks, this one is actually designed for flash storage.
It's designed for flash storage, and by the looks of it, designed for very high heat-producing flash storage at that.
Something you might not think about in a traditional server is a lot of graphic power, but that's something that Facebook needs. Let's take a look at this graphics sled, William. Show me what we got going on.
So we got this sled, it's called the Big Basin. It's what they put 8 graphics processing units in. So if you see here, we've got all the power delivery stuff in the back, which if you look is an insane amount of power delivery going on. And this is based on NVIDIA's reference design for their P100 platform. And you can see we have 8 different GPUs inside of this tray. And they all connect over PCIe, and in the NVIDIA case, they do have NVLink connections between some of them. And you can see in the back, we have the PCIe switches, which interconnect all of this, and it exports PCIe out the front here via these little cards, which in some cases have retimers, and in sometimes they're just really simple, dumb pass-throughs of PCIe.
What's interesting about that is a lot of the Open Compute Rack is designed around commodity hardware, is designed around standard connections. So this is just a standard PCIe slot, and in this case they're using it for an interconnect to the rest of the sleds, but you could use it to add a network card, you could use it to, I assume, even add a graphics card.
Yeah, so what's really interesting is you'll notice this tray only has GPUs. There's a management controller in the back to make sure the fans are running, to make sure the GPUs are actually up and online, and just to sort of communicate with the rest of the health status network. But there are no CPUs in here, and so they actually use the PCI Express over these connectors to the host machines in the rack in order to do any useful work.
So we're making our way down the rack. Now we showed you the 15-disc regular hard disk controller. We showed you the flash controller. William, let's go ahead and open this one up. This is a monster 72-disc hard disk controller. William, tell me about this.
Yeah, so this is what they call the Bryce Canyon version 2, and this holds 72 different independent SAS hard disks. And you can see here, they're all stacked vertically, and the back plane is kind of down in the back. And it has 2 different machines to control it. So it controls the front 32 disks as one machine, and the back 32 disks as a separate machine. They've just put it all in one location so that it's easy to maintain. So let's start taking this thing apart. All right, so in here, in this center area, we've got the power cabling, and you'll see if you push it in and out, it actually unrolls in this little plastic guide that they've got going. And you'll see we also have these trays with these very interesting looking connectors, and the connectors are feeding SAS or SATA, depending on what types of disks you have, to the disks, and then they're feeding PCIe from these SAS controllers that are located on this board back to the host machines in this front part of the unit.
Now the interesting thing about this cable unit that's rolling up and rolling out is that this unit can actually stay powered on as it's being serviced. So as it rolls out, we talked to you earlier about the power rail that runs underneath for some of these units. This would not work in this particular case because of the sheer power requirements to run 72 disks. So they actually run separate cabling inside of here so that this unit can stay powered on as it's being de-racked.
Yeah, that's right. One of the goals of all the equipment here is to be able to have it as maintainable as possible while also preserving uptime. So in almost all cases, you can pull all the units almost completely out of the rack and service individual parts like swapping disks or swapping even PCIe cards and those sorts of things without taking the unit offline. Or in the case where you have multiple machines, which I'll show you later, you can pull one machine out of the tray without powering off the other machines that are also in that same tray.
William, let's go ahead and dig into this. I want to see what's underneath these pieces here.
Yeah, so under here, we actually have both of the management computers. So these are x86 machines, and you'll see later these are actually taken from a similar design that is just meant for compute. So these guys, you get a single, most likely Xeon D, we're looking at some kind of BGA product under there, machine with 4 different DIMMs, probably 2 DIMMs per channel, 2 memory channels, that sort of thing. Right now it's populated, as you can see, with 2 sticks of memory, and it also has support for an M.2 boot drive on there.
But this is essentially, it's an entire computer, right, in one unit?
Computer. That's right, it's an entire computer. You can boot this. If you just provided power and maybe networking, you could boot this and use it as something without the rest of the disks. So it's acting as the host so that you can get these disks onto the network, and it plugs right into the backplane and then hooks up to the SAS controllers over PCIe.
If those self-contained computers interests you, they have an entire sled for those. Let's go ahead and pull this out, and William will show you. This sled contains up to 4 of those compute modules, and we'll dig into exactly what's in every one of these, but there's essentially a backplane that connects all these together, isn't that right?
That's right, so if you look underneath these modules, there's a little baseboard with a management controller and a NIC hooked up, and that connects all 4 of these computers to the network using kind of their centralized infrastructure. And something to note in the rack here, you can see from the unit that was taken out, there's actually a power rail that runs all the way from the back to the front of the machine. All of that is solid state, so you don't have like an extra cable wiggling around, and that provides power to these machines even when the unit is pulled all the way out of the rack like this. So when we pull it out this way, it would still stay on, and you could pull an individual machine out and service it without taking the other ones offline or even disconnecting them from the network.
Okay, so we've pulled one of these compute sleds out, and we now have it sitting on a table, so let's go ahead and pull out one of these computers and tell me what's inside of one.
Yeah, so if you look, this again is fully toolless. We can grab the machine, we can just pull it right out by opening these latches, and that allows us to service the individual unit. So you'll see this unit is very similar to the design of the one we pulled out of the storage server. It's got that individual machine, and it's flanked by 8 DIMMs in this case. This is actually one of the newer ones. And you'll see it's all self-contained, and on the back, we don't have storage on the front this time. We flip it over, we go to the back, you'll see there are these metal shrouds where you can put M.2 cards, and in this case it has 3 of them. And again, toolless, you can pop these right off by pulling on the connector tabs. That would pop it off and expose an M.2 connector. And then it's seated using the same 2 PCIe looking devices, and then it just goes right back in the way it came out.
So each one of these sleds essentially contains 4 independent servers that contain storage, it does processing, it does memory, the whole 9 yards are all contained in each one of these units, and then it connects to a backplane. Now it's interesting, these devices actually are sharing a single NIC.
That's right, so there's going to be one network interface cable coming in on the one NIC on the front. You can see there's a single port. That will be for your BMC and for all 4 nodes, and they'll roughly share about 10 gigabits per node. I think this might be a 40 or 50 gigabit NIC in here.
This is absolutely a better way to build a mousetrap. This was a very cool piece of technology, and a huge congratulations to not only the Open Compute Project who are designing this, but companies like Facebook and Google and all of the other companies that are putting these in their data centers, because they are fundamentally changing the way that we do servers and data racks. I mean, what do you think, William? Pretty cool, right?
Oh, I think it's absolutely cool, and it's absolutely going to replace the way people do things in the data center. From Minddrip Media, this is William Kennington.
Hey, and I'm Noah Chalai. If you like this video, check out the Ask Noah Show. It's a weekly talk radio show where we highlight more Linux and open source technologies. You can catch it every Tuesday, 6 p.m., asknoahshow.com.